Good afternoon, everyone. If you want to take a moment to take your seats, we are about to get started with our next speaker. My name is Dr. Talithia Williams, and I am a statistician in the mathematics department at Harvey Mudd College. And it is with great enthusiasm that I get to stand before you today to introduce a luminary in the field of statistics, and my dear friend, Dr. Kimberly Sellers, who currently serves as the head of the statistics department at North Carolina State University. A DC area native, Dr. Kimberly Sellers completed her bachelor's and master's degrees in mathematics at the University of Maryland College Park, and then she went on to obtain her PhD in mathematical statistics at the George Washington University, partly supported through that program as a Gates Millennial Scholar. Dr. Sellers also held previous faculty positions at Carnegie Mellon University as a visiting assistant professor of statistics, and also at the University of Pennsylvania School of Medicine as an assistant professor of biostatistics and a senior scholar at the Center for Clinical Epidemiology and Biostatistics. Dr. Sellers is an elected member of the International Statistical Institute. She's also a fellow of the American Statistical Association and a fellow of the Association for Women in Mathematics. But beyond her scholarly achievements, she really stands as a beacon for diversity and inclusion in the STEM fields. She was the inaugural chairperson of the ASA's Justice, Equity, Diversity, and Inclusion Committee, JEDI. She also chaired the ASA's Committee on Women in Statistics, and she continues as an advisory board member for the Black Doctoral Network, which she's done since 2012. She's also garnered critical acclaim for her groundbreaking work in generalized statistical methods, particularly those dealing with count data exhibiting dispersion. Her expertise extends to image analysis techniques with a focus on low-level analysis such as pre-processing, normalization, feature detection, and alignment. The significance of her contribution is underscored by her authorship of the recent book, The Conway-Maxwell-Poisson Distribution, which was released to critical acclaim in March of 2013. Without further ado, I invite you to join me in welcoming Dr. Kimberly Sellers as she takes us on a journey through dispersed methods for handling dispersed count data. Dr. Sellers.
My goodness, thank you so much, Dr. Williams, for that impressive introduction. And thank you to the committee members for offering me this opportunity to present to you today. As you can see, and was referenced, the title of my talk is Dispersed Methods for Handling Dispersed Count Data. And so what you will see today is an introduction to the varied ways in which I and others have had involvement with how to analyze discrete data. Okay, so recognizing that I am speaking to a very diverse audience, let me first offer context as a baseline, introducing you to the Poisson distribution, which is a classical statistical distribution for measuring or describing variation in count data. And so for some rate parameter lambda, we have the following probability mass function that's presented here. And for those of you who, if you've taught, say, an introduction to statistics course, at least I know I'm good for doing this. The way I describe the distribution is by saying, if I know that value of lambda, I actually have a great amount of information. In particular, I know both the mean and the variance of this distribution because they are both that value lambda. Stated in another way, we can represent this as saying that the goodness of fit statistic, measured by the ratio of variance to mean, is equal to 1, or what is referred to as equidispersion in this space. So for context, the issue or motivating matter surrounding consideration of this larger problem, is that most real data do not conform to this idealized representation of equidispersion. And so this can have several implications as it relates to statistical analyses and inference and trusting the results of your efforts. If we focus our attention on the notion of over-dispersion, meaning that the variance is larger than the mean, that is your more common reference point in real data. And so, as you can see, we refer to this with the goodness of fit measure as being greater than 1. The most popular distribution for handling such data is what's referred to as the negative binomial distribution, presented here. For those of you, depending on your measure of statistical exposure, the negative binomial is a generalization of a geometric model, which asks how many events have occurred until you obtain R outcomes of interest. And so under this construct, we have the mean and variance represented as follows. And so as you can see, given those resulting measures for the mean and variance respectively, it's clear that the variance is greater than the mean. Okay, so again, this winds up being a very popular distribution for handling over dispersion. And so as a result, the distribution is very well studied. And there's a lot of work addressing statistical computations associated with this distribution, be it in R, SAS, or some other software. However, the drawback to this distribution, if you noticed with those values for the mean and variance on the previous slide, it can only handle over dispersion, or at best, equidispersion. So if your data are under dispersed, then the negative binomial does not have the capability to address such relationships. And so why is this an issue? Because as we're looking at more and more contexts with real data, we're seeing more and more examples of data under dispersion coming to existence. And so, of course, there's the need to address it. While there has not been but so much study as to the causality, if you will, behind such results, there have been various attempts to understand the motivating derivation behind such measures of underdispersion. As you can see here, be it the Puig et al. Paper in 2016, or for example, even going back further with Barlow and Prashant as an example of the underlying stochastic process that could envelop such a construct. However, there are others that still would argue that such a relationship is not necessarily meaningful or truthful. And so, nonetheless, the approach that I and others take is instead of asking about the validity of such data, there still begs the question of how to properly analyze it. And so one option for consideration is what's presented as the generalized Poisson distribution. This is a two-parameter generalization of the Poisson model where if we let lambda 1 represent that Poisson rate as was described before, lambda 2, meanwhile, describes or serves as a dispersion parameter. And so for this value, lambda 2, if you let the value equal 0, then you can see that the distribution reduces to a Poisson model. And then meanwhile, when lambda 2 is greater than 0, it can accommodate for overdispersion. For lambda 2 less than 0, it can handle underdispersion. However, the limitation to this distribution is actually as recognized in some references associated with this model that actually go so far as to refer to it as a restricted generalized Poisson, because as you can see with the, let's see, can I point? In the latter case, you'll notice a constraint with the distribution. And so for certain values of lambda 2, it can only be so sufficiently small for accommodation. And it turns out that with further study, in the extreme cases of underdispersion, what can happen is that the distribution can crumble, if you will, violating probability axioms. And so this, of course, presents as a drawback to a statistician. So the question then becomes, is there an alternative approach for handling data over or under dispersion? And I will present one such model to you today. But to first motivate why one is interested in this approach is because if we can remove concerns about dispersion in our data analysis, or not remove it, but account for it, then we are providing a means by which to better assess and understand the variation that is existing in the data and trying to capture the uncertainty that exists as a result, thus demonstrating better inference. And so what I present to you today is an alternative two-parameter model called the Conway-Maxwell-Poisson distribution. The Conway-Maxwell-Poisson, or COM-Poisson for short, is a distribution that was initially introduced by Conway and Maxwell in the 1960s, where they developed a generalizable queuing process for consideration that, was introduced through this secondary parameter nu, which is serving as our dispersion parameter. And so for this value nu, you'll notice it's a non-negative value, where for nu equal to 1, we capture the Poisson model as a special case, so we capture data equidispersion. But for values outside of 1, think of this as an inverted relationship. When nu is greater than 1, we capture data under dispersion. For nu less than 1, we capture data over dispersion. Meanwhile, we have this normalizing constant z, or normalizing function, if you will, that you see is an infinite sum to allow us to maintain our probability axioms, ensuring that the sum of all of the probabilities sums to 1 over our parameter space. Meanwhile, nu, as you can, or sorry, lambda, is the nth moment associated with x. And so what's also interesting with this model is that it not only captures the Poisson as a special case, but it captures two other classical distributions, namely the geometric and the Bernoulli models as other special cases. As you can see, when nu equals 0 for lambda less than 1, of course we need lambda to be less than 1 to ensure that that infinite sum converges. We obtain the geometric model with success probability 1 minus lambda. And when nu goes to infinity, we wind up with a Bernoulli model with success probability lambda over 1 plus lambda. And so what's nice about this model is that here we have, simply by the introduction of one extra parameter, we have a general model that bridges 3 special case distributions and captures dispersion of varying types in between. So think of the COM-Poisson as this umbrella overarching distribution. Here I present you with an example of, that demonstrates some of the flexibilities of the COM-Poisson distribution, where you're seeing different representations for the distribution for different values of nu, at least for the most part. You'll notice for 5 of the 6 figures, we maintain lambda at equal to 3, but with the upper left picture, lambda equals 0.3. Again, I remind you because we need the case where lambda is less than 1. And so here you can see how the distribution is spread more widely for values of nu less than 1, and then that distribution seems to be more compressed when nu is greater than 1, representing the under dispersion. Okay? Meanwhile, we can see our special cases illustrated here. For the case where nu equals 1, this distribution is our Poisson distribution when lambda equals 3. In the upper left-hand corner, we have the case of a geometric model with success probability 0.7. And this third case, if you notice, what you are seeing are simply 2 bars in this distribution, one at the value of 0 and one at the value of 1. I recognize that the font is considerably small, but trust me when I tell you, if you look, you will notice that it represents that Bernoulli model. And so what's interesting in this case is that I remind you of the theory versus the reality here. in theory, nu should go to infinity, thus obtaining a Bernoulli model. However, notice nu didn't have to take so long to get there, right? It only took a value of 10 to represent the Bernoulli representation. And we'll see other illustrations of that as we move forward. Some other properties of the model will bring back, hopefully, pleasant joys of any former statistics grad student, take you back to your math stat days, and some of the various properties that you would have learned in your math stat courses. As you see, here's an example where the Poisson likewise satisfies an exponential family form, where we can recognize the joint sufficient statistics for lambda and nu. And we can likewise have a representation for the expectation and variance of this distribution. Now, what's interesting in this result is that, of course, what you're seeing here is that the mean and variance do not have a closed form. This is a common concern raised among some researchers that will try and argue against this model. In contrast, what I offer is that in this space of computational knowledge and complexity and strength, that argument is somewhat weak at this point. So, and as you see, there are approximations that exist for it. However, one does need to be mindful about the constraints associated with those approximations, depending on how much precision one wishes to entail for these moments. Here, I'm just offering a glimpse of some of the various packages that have been developed, at least in R, for calculations relating to the Poisson distribution. And this is under what I'm referring to as the CMP parameterization. I'll explain how I'm differentiating this from other parameterizations in a second, but the original parameterization that I presented to you is what I will present as CMP. And for those of you taking score, that one's mine. And what's also interesting is that other packages have also picked up on this distribution. As you can see with SAS, they too offer the capabilities to compute the distribution under multiple forms as well. I have to give a nod to SAS as a NC State representation. Okay, so other parameterizations that exist for the CMP are as follows. There are actually three that have been recognized. First is what I'll call the approximated CMP. I refer to this as such. And what they do is take a measure of center. Notice I'm not calling it the mean. A measure, a representation of center, where they define it as lambda to the 1 over nu power. The significance of this distinction, as I've described it, is because I'll remind you, the definition of the mean was actually this. Okay, so notice what they are doing is already taking an approximation for the mean and further truncating it for an easier representation for calculation purposes. Okay, and that's why it's so important to stress that this is not the mean. But nonetheless, under this representation, we have the following parameterization. And it's important to note that this is represented or proposed only for over-dispersed data, because if you recall, the approximation that I presented to you initially for the mean required the data to either be over-dispersed or for lambda to be sufficiently large relative to nu. Meanwhile, another parameterization for this model is what's referred to as the mean parameterized Poisson distribution. To explain the premise behind considering these different parameterizations, it's because there was concern expressed regarding the initial parameterization, and that if one wishes to move this model forward and consider, say, a regression model, oftentimes in generalized linear model, in the GLM framework, one is interested in relating the mean to certain factors, okay? So what they're doing is trying to restructure the distribution in a way that will allow them to move forward in a regression context. And so in this case, what happens is they do have a representation for the mean, but notice that they can't write it down, okay? We saw that before because we had this non-closed form representation for the mean. Nonetheless, we know that a value for the mean exists, and we can think of lambda as being a function of both the mean and our dispersion parameter. And so here the authors has represented the parameterization in that way. And so under this construct, what we see is that it makes sense that it too can satisfy the special cases in a restructured way such that everything is centered around this value for mean. So it has the Poisson with a rate parameter of mu when nu equals 1. We have a geometric distribution with success probability 1 over mu plus 1 when nu equals 0. And the Bernoulli has success probability mu in the case where nu goes to infinity. Meanwhile, the last reparameterization, what I call MCMP2, takes a different approach that simply says, let's work from that approximated mean that we saw noted in the CMP case and use that as an approximation of mean, if you will, along with the dispersion parameter in such a way that we can reparameterize it accordingly. Again, here, I remind you just to be mindful of the constraints of the parameter space for which this approximation makes sense. And so here are just some of the packages that have been developed based on those model formulations as well. And so with this in mind, irrespective of which representation from which you work, there's been a lot of study developing statistical methodologies surrounding or motivated by the Poisson. Today, I'll discuss 4 of these areas: regression analysis, control chart theory, stochastic processes, time series, and spatial temporal analyses, and lastly, multivariate distributions. First, focusing our attention on regression analysis, we have the following. Irrespective of your parameterization of the CMP, what one can do is develop a generalized linear model construct that relates both this rate parameter, if you will, or intensity parameter that I have generally recognized as theta, and the dispersion parameter nu in relation to some variables or factors of interest. For the particular case of the CMP construct, what we found is that under that parameterization, what was particularly interesting is that just as the distribution captured 3 special cases of 3 special parameters, special distributions, the regression form likewise captures special cases. And so this Poisson regression captures the Poisson model and a logistic model as special cases. For those unfamiliar, the logistic model is simply a regression that asks about a response variable that has only 2 possible outcomes in relation to some variables of interest. And so one can imagine as well a third representation, if you will, a geometric regression, which is actually simply a special case of a negative binomial regression. And so for the MCMP1 parameterization, it too captures those special cases, but directly in relation to the mean. And that is the one distinction from the CMP construct, because I remind you that lambda in that parameterization is not necessarily the mean, except for the special case of a Poisson. However, for the other parameterizations, again, you have to use caution based on the constraints that were previously presented. Some extensions that have been done in relation to this work include consideration of excess zeros. So if you have a lot of response outcomes where the outcome value is 0, then that has to be accounted for to properly assess or model the relationship and variation. And so in that case, we have a third model, this logit, in this case, illustrated to consider zero inflation, but one could alternately consider a hurdle model to capture the excess zeros. And meanwhile, there's also been work done with cluster data analysis through random effects to, again, account for those scenarios. Here we have some of the many packages that will allow one to account for regression in the Poisson space. And likewise, SAS has the ability to conduct a simple regression or a zero-inflated model regression as well. Meanwhile, if there's interest in pursuing a cluster data analysis approach, one can do so through the use of proc-NL mixed in SAS. Here I have the illustration for the case where one considers a random intercept model. And so some simple illustrations of these models are as follows. Here we have an example where we're looking at air freight breakage, a collection of jars that have been broken over a series of flights. And if you look at these data, what you'll find is that they are underdispersed in relation to each other. And so if one asks to compare, in this illustration, we're looking at a Poisson model with either a CMP or mean parameterized CMP model. What is interesting here when we compare models is the following. First, let me bring to your attention let me caution you against simply comparing all of the respective values across the rows, because for much of this, these are apples to oranges comparisons. However, what you can see is if we look at AIC, the Ikeki information criterion, the goal here is to have the model with the smallest AIC. And while the Poisson would be the traditional approach for modeling such data, since we're counting the number of jars that are broken, what you can see here is that the Poisson model has the largest AIC. And meanwhile, the CMP, and whether it's CMP or MCMP, you can see those perform better relative to Poisson because it's capturing that data under dispersion. And here, what we're seeing is that effectively captured again, because on the log space for new, I remind you, when new was greater than 1, we captured data under dispersion. So here you're seeing consistently positive values for new, where these software packages are recognizing the under dispersion in the data. Another illustration here to account for excess zeros is an example that's been frequently studied, looking at the number of unwanted pursuit behavior perpetrations, where this is a case where several couples have been analyzed, and it's asked how many such perpetrations have been enacted in the scenario, and thankfully, most of these are zeros. However, nonetheless, there is some counting measure that is occurring. Here, for illustrative purposes, we are building a regression that asks about education level and level of anxiety, where anxiety is a continuous measure while education is categorical, and how each of those factors affect or associate with each the intensity and measure of zero perpetrations. And so what you're seeing here are various models that have been considered for analyzing the data, all of which are accounting for excess zeros. Those that are prefaced by ZI are saying that the zero inflated analog is being considered, while the H reflects the hurdle model. And so what you can see here is that for any of the, shall we say, alternative models, alternative to Poisson, we have better performance relative to the ZIP model. But it's interesting to understand how they compare with each other. So first, notice that for the count component, we can compare the zero inflated and hurdle models that are both based on a mean parameterized CMP, because of course that base construct is considered from the similar parameterization, namely MCMP1. So it makes sense that those numbers match. Meanwhile, it also makes sense that if we compare across zero inflated models, that those estimates, likewise match. But what's also interesting here is that while in this data set, you saw that the negative binomial ever so slightly outperformed the other models, What was also telling is that for the dispersion estimate, notice that that value is consistently 0. The fact that the value is 0 is, again, very telling. This, remember, is a special case where it says the composite is, in fact, a geometric model. So utilizing CMP now as an exploratory tool, it's giving us the ability to constrain the space of consideration down to, if you will, a zero-inflated geometric model. And by doing that, I've now reduced the number of parameters necessary for estimation and thus created a more concise model. And you see it outperforms the negative binomial as a result. A third example for consideration is this epilepsy data set. Here it's to illustrate how the composite can be used in a space for clustered data. And so we have a scenario that's counting the number of seizures for particular subjects across different periods of time. And again, various models have been considered where the essence of the regression form, as you can see, is supplied here, where we're looking at various indicators of interest along with the length of time for model consideration. And so in this case, for simplicity, we're only illustrating the random effects models under Poisson, negative binomial, and CMP respectively. And what's interesting here is that while the data are over-dispersed, notice that the CMP model actually outperformed the negative binomial. This was an interesting case for illustration because in most cases where the data are recognized as being over-dispersed, one has found that the negative binomial was still the top performer. And so oftentimes researchers question the need for this sort of more flexible model that accounts for dispersion if one knows that the data are over-dispersed. Yet here, like I said, is an interesting example to counter that narrative. Moving on to control chart theory, this area of work, I'm humbled to say, as it relates to composite, was started by me. So it's always nice to go. It demonstrates the value of attending conferences because I can tell you I sat in a talk and they were going on about a Poisson control chart, and this is when I was early in my composite interest and literally sat there thinking through how to generalize everything that they were discussing. And so this was my motivation to develop this flexible control chart based on, at this time, I was keeping it simple, considering, if you will, simply Shewhart bounds for the constraints, for the bounds, upper and lower bounds respectively. And a moral to the story that I will share with you because we're family. A lesson that one should learn is the following. Never do what I did in this paper. What did I do in this paper? In my discussion section, I explained that while this is an easy way to gain initial estimates, what it is doing is producing symmetric bounds, and it's known that the distribution is not itself symmetric. So what would be more proper is to actually obtain probability bounds related to this distribution to have a more precise representation of upper and lower constraints. And I go on and sign off on the paper, submit it, it gets published, and I think to myself that I'm going to get back to this one day, but I'm trying to move on with other work as we often do as researchers. I'm sure you can imagine what showed up on my desk about a year later to review. A paper that has done probability bounds relating to composite and how the precision has been improved as a result. So of course it's natural to send it to the originator where they call it the seller's chart, no less. So the blessing here is that there is something called the seller's chart. The curse is that it's always negated, but I'll take it. Okay, but yeah, so this was the first of many. Oh, and the other piece was, as future work, oh, this is just the beginning of an obvious array of opportunity related to control chart theory. Someone heard that too. As you can see, there's been lots of work done in the space of control chart theory relating to Poisson. Here is just a list of the many works that I've done in terms of exponentially weighted moving average models, or EWMA. And similarly, there's been a lot of work done with Q-sum charts. In all of these works, like I said, they always reference the Sellers chart as the base model and then move on from there. So go figure. There is the Sellers chart. And I didn't name it, by the way. Thirdly, we have the area of stochastic processes, time series, and spatial temporal analysis. With regard to stochastic processes, there's been a few works done. The one that I will elaborate on today is the homogeneous CMP process, because this is work that I did with one of my, the first author here is a former undergraduate that was working with me along with a master's student in this project. And so I'll discuss some of what we did here. In this work, we are generalizing the Poisson process to allow for, again, flexibility in the relationships and the steps. And so what you're seeing here is a consideration that at each step, to consider the probability, we're framing this based on a Poisson model now. And so as such, everything that you're seeing here generalizes the Poisson model or Poisson process, and similarly generalizes the Bernoulli process, because remember that too is a special case. More broadly, this turns out to be a special case of what's referred to as a weighted Poisson process, and it generalizes other particular works relating to stochastic processes. What was most interesting in this work was discussion of a waiting time when we're considering this construct in relation to our normalizing function z. What is consistent in this representation is the representation of the waiting time function through its cumulative distribution form, as you see here. But what makes it interesting is to ask what then is the resulting distributional form relating to this CDF. And that depends on how you think about the waiting time. If we consider the waiting time to be continuous in nature, then notice we can view this as a special case of an exponential distribution, if you will, COM exponential, because it's based on the normalizing function z. However, if instead we consider discretized forms of counting waiting time, it turns out that this generalizes the geometric distribution. And so this winds up being a very interesting construct demonstrating the flexibility of this model, whether you think of waiting time in a discretized or continuous fashion. The work here has also been established into an R package, as you can see here, so that analysts can use it to analyze their data, whether they have frequency data or time to event data for consideration. Moving on to time series and spatial temporal analyses, there are two general approaches for constructing time series models. The easier of the two was not done by me. These are what I've referred to as intensity parameter time series models. In other words, what was done here is that they are considering models in relation to that intensity parameter, lambda, and building a model off of that in a continuous fashion, and then carrying it forward with some accounting for dispersion as well. The reason I say that this is the easier approach is because lambda can be a continuous value. Okay, so it allows for the traditional flexibility of modeling that form. That construct is actually carried forward in the spatiotemporal space as well. Because apparently I don't like to do anything easily, I and others have considered what are referred to as thinning-based models. In the thinning-based model space, what you're doing now is inherently accounting for and considering the discretized nature of your process and maintaining accountability for that at each step. And so I'll explain more of what I mean here in the coming slides, but nonetheless, what you're seeing is that there have been some preliminary works that have considered the one-step models, be they autoregressive or moving average forms, and likewise univariate or bivariate as well, or multivariate for these spaces. And so, as you can see, there have been various works where they differ depending on what is used for the innovations, meaning how many, taking into account how many, let's say, people or outcomes of interest enter into a time series model at a particular step. They differ based on the thinning operator. In other words, moving from one step to the next, how do you move from one count to the, not everyone necessarily moves on to the next step. And so how is that modeled? And thirdly, how one estimates the model for consideration. Focusing on the works in which I've been a co-author, for the first order autoregressive model, we have the construct where, we are looking at innovations that have what I refer to as a sum of composons, because I couldn't come up with a more clever name. But this accounts for the distribution of the innovations. And meanwhile, we have a generalized COM binomial model that takes into account the thinning from one step to the next, and build off of this to account for the number of outcomes at some time t. With that construct in place, you can see the transition probability that results, and now appreciate what I meant when I said apparently I don't like to do anything easily. While this is a complex form in nature, thankfully we have computers to do the heavy lifting for us. And as it turns out, this resulting Markov chain is ergodic, so all steps can be approached at some point in time, and it also has a resulting unique stationary distribution. Meanwhile, we have a form for the joint probability generating function, and can thus see that the distribution is time reversible. There's a form for the expected value at a particular step, and we have a form for the correlation. Meanwhile, for the moving average model, we likewise have a form that generalizes, again, classical moving average time series models of a discrete nature, be they the Poisson, negative binomial, or binomial distributions, respectively. Further, we can likewise recognize it as being a stationary process, where since we're now dealing with a one-step moving average, we find for 2 or more steps, there's independence between the outcomes. We again have a form for the correlation. And it turns out that there is a relationship between the one-step moving average versus autoregressive models, respectively. And so with these 2 models in place, they can serve as building blocks for developing more exquisite models, say autoregressive moving average or ARIMA models, respectively. And through data simulations, we can see that we can produce unbiased estimates of interest and obtain work for forecast models. Moving into the last space for consideration, multivariate distributions. The idea here is, of course, to consider distributional forms that allow for correlation among, say, random variables. For illustrative purposes, I'm going to simplify the process to simply a bivariate form for simplicity, but at least some of these works have been generalized to D dimensions. The first model for considerations was referred to as a compounded bivariate composon. And this is produced by taking a bivariate binomial model with some given number of outcomes or trials of interest, say n, and letting that value n be modeled by a CMP model. And as a result, we have obtained the joint probability function and the ability to recognize that it too captures or generalizes 3 special cases. We have the Holgate bivariate Poisson when nu equals 1. We have the Marshall and Olkin bivariate Bernoulli model when nu goes to infinity. And thirdly, it captures a bivariate geometric model. And this work, we went on and started producing a larger R package to capture this and other generalized multivariate distributions. Now, if I can go back to this compounded bivariate Poisson, what was interesting in this space as a positive is that it captured 3 special bivariate models as special cases. However, what was interesting is of course the complexity that came with it. And so instead, we consider what we've referred to as a trivariate reduced bivariate CMP to ask, if we consider the more simplistic model here, what does this afford us? And so what we have here are considerations of 2 random variables where they are clearly correlated by a random variable, what I've denoted W12 here. So they share that random variable in common. And so obviously there is a codependence there. And so the question becomes, what happens under this model construct? And so here we have the joint probability and joint probability generating functions, respectively. And notice that it too captures special cases, but not in the same way as the compounded approach. So while they both share the bivariate Poisson, the alternative special cases are as defined here. Meanwhile, it's worth noting that their marginal distributions can at least be identifiable for special cases. So we do capture Poisson marginals in the case of Poisson equidispersion, and meanwhile we have this sum of compoissons under the condition presented here. So while again we have progress in these 2 bivariate models, what's important to note here is that one property that exists for both of them is that the correlations associated with those models are always positive. And so it begs the question if we can produce a model that allows for positive or negative correlation. One attempt to do so is through these Sarmanoff constructions, where Ong et al. Considered the following representation for constructing the bivariate model. Under these approaches, the parameters phi, respectively, can be represented in the following manners, and they produce the respective resulting correlations. Those correlations that are presented there do allow for positive or negative correlation. So at least on the surface, it looks like there's further advancement in the space to allow for positive or negative correlation here. Yet another consideration to allow for better flexibility would be cupulas. As you may recall, there was a lot of attention focused on cupulas at one time to generalize various distributions in the multivariate space. And a lot of that was due to Sklar's theorem, which said that a cupula function exists such that the multivariate form of the CDF can be constructed based on a cupula, and that cupula was unique. However, it's important to note that this is the case for continuous random variables, but not for discrete ones. Okay, so for the purposes of illustration, I will dismiss any further consideration of cupulas here because, in fact, there are infinite ways in which one can utilize a cupula to develop a bivariate CMP. But here I will illustrate an example considering the various models considering NBA all-star players, and how many of them are either forwards or centers or both on their teams. And the data are analyzed considering a bivariate Poisson, negative binomial, generalized Poisson, and then the various CMP models that have been considered, be it the trivariate reduced form, the compounded form, or the Sarmanoff 1 or 2 functions, respectively. As you can see, what's being presented as a result are the respective estimates based on maximum likelihood estimation, along with their resulting log likelihoods, the number of parameters required, which is needed to obtain the IQ key information, and then this last column, delta, provides information regarding simply the difference in the respective AICs from the minimum AIC to help for model comparison. So what are we learning as a result? As it turns out, that simplest model was in fact the best performer here. Meanwhile, we further see that the data are under-dispersed, because notice that the estimate for nu is greater than 1. And so with that narrative, notice that all of the generalized distributions that allow for under-dispersion outperform the Poisson and the negative binomial. To explain why that's the case, think about, let's take my arm representing as the space of equidispersion. Above my arm represents overdispersion. Below my arm, underdispersion. So the data are falling somewhere down here, okay? But your Poisson model can only land somewhere on this line, so obviously it can't get down to the bottom. And meanwhile, for a negative binomial space, it's bouncing around trying to get down here, but the best it can do is at my arm, right? Why? Because remember what I told you before, it only allows for data over dispersion. It cannot capture under dispersion. So it turns out that the best it can perform is precisely that of the Poisson model. And so that's what you're seeing here, but you're actually seeing more than that. The fact that we've introduced an added parameter to the model only to get similar results is only hurting us because we're incorporating more information. Okay, so in the end, what we saw was the composite outperforming the other models, in particular the trivariate case. With all of this said, I've only scratched the surface regarding all that can be done with the composite distribution. And if you're interested to learn more, feel free to go downstairs and stop by Cambridge University Press booth. They do have the copies of the book for sale for the low, low price of, no, I'm not sure how much, but it is down there. And as you can see through the table of contents, there's been a lot of work done in the area. And in particular, just to illustrate how work is still ongoing, I'll focus attention. You saw some, I slipped it in various ways in the talk today, some introduction of different distributional extensions and generalities, just to give a taste of how this is still ongoing work. In particular, I like to work a lot with, of course, undergraduate and graduate students, undergrads in particular. So I just directed a summer program this past summer where in my group we were looking at one of these extensions and actually recognize some additional properties associated with it, and I had the students develop an R package for the process. So I say this to say not only is this an opportunity for advancement in research, but advancement in mentoring to students at all levels. And so to close out, I just want to acknowledge the many students. This is just a snippet of the many students and collaborators that I've had through the years working on this work. Actually, the picture in the center is that summer program from this last summer. So with that, I thank you for your time.
Fantastic. We have a few minutes for questions, so if you would like to ask a question, there are 2 microphones in the room if you want to head up right now. I'll kick us off with a question. I was curious, what's the difference between the R packages that you developed, in particular the first one that you developed, compared to the ones that were currently sort of available to analyze that data?
Wow, great question. I'd say the biggest difference is in terms of their offerings. So this is the blessing and curse of working with a model that is garnering attention in real time. I think we've all heard that narrative, publish or perish, right? We're all too familiar with it. And this is an example where that is very true. And so many of these packages for example, were established concurrently. And in fact, even that initial regression package, as an example, is one where regression, I didn't get into this in the talk, but there were 2 regression works that came out around the same time. And I'll just simply say that my heart is still functioning as a result, because it's very emotional, shall we say, and very anxiety producing to worry that your work may be circumvented because of someone else's work potentially preceding yours. Yeah, so it's in similar form with the R packages, what you'll see is that they don't all, they differ in myriad ways. So they differ in terms of their offerings, they differ in terms of their approach for estimation, and yeah, I'd say those are the 2 main areas, but there are other subtleties as well.
Yes.
Yeah, Dr. Saylor's wonderful talk. I was really intrigued by the data that you had here for the NBA players. And in particular, I started to think about a lot of the interest nowadays in data analytics. Do you have any idea, any intuition behind whether any of these packages that you're using with these generalized Poisson distributions might be more readily used by people who are interested in data analytics?
I'm happy to say that there is growing interest. In fact, I'd argue that that is probably where I've gained more notoriety than the theoretical work itself. In particular, with the regression model, I've received my share of emails thanking me for producing a package that can allow for data under dispersion. And invariably, the narrative is the same. These are usually analysts that recognize that their data are under dispersed, but they can't find they couldn't find an R package that could properly analyze their data. They knew that the results that they were getting weren't necessarily the best, but they didn't have a better means to address the matter. And so what usually happens is the thank you starts there and then continues on to say, so that said, can you go on and make it now do X, Y, Z so that I can make it do even more analyses? And of course, the blessing and curse there as an academic is trying to satisfy the needs of your constituents, but advance the research at the same time. So it's been an interesting space, yeah. But I'd say I think I have maybe 5 R packages total. My regression one is hands down the most popular, and it's for the reason that you just demonstrated.
In the very first example you gave, you highlighted, I think it was the natural log of new parameter, but you weren't able to get standard error estimates for it. Why
right.
is that?
So I'm happy to say that wasn't my package. My package gives you standard errors. But so that's one of the ways in which there are distinctions with from different works. And it depends on which pack. I mean, we could always go back to check. But I can tell you the difference was some packages do not report standard errors, which of course we know as statisticians to be an issue because we want to be able to recognize and quantify the uncertainty associated with an estimate. Or I think in one of those examples, you actually saw an NA for the standard error. And what we at least hypothesize as being the issue there is that through the optimization procedure that was happening under the hood, it crashed somewhere in the process and thus was unable to report a standard error. Yeah.
Can we thank Dr. Sellers once again with a round of applause?